Good afternoon, at least for me. Wanted to talk a little bit today about eddy current, some of the uses of eddy current, some of the applications of eddy current, stuff like that. You've seen most of the stuff online already that talks about eddy current, kind of where it comes from, what happens, all that. And we have, at least I have been, hopefully you have as well, been through a lot of the information talking about James Maxwell and Hans Christian Ørsted and all those guys talking about where eddy currents come from, how they're made, all that kind of stuff. So let's just talk about that basic setup one last time here. You looked at that first PowerPoint that talked about eddy currents coming from eddies in streams, kind of where they all come from. So if we were looking at an eddy current setup here, we would say that we've got a coil here, okay? That's connected back to a scope somewhere back in the back. Okay, we don't really care about that right now. What we care about is the terms that actually make this all happen. Okay? We know that there's a couple of terms in there that are always happening, like inductive reactance. Then we've got plain old resistance. Then we've got impedance. And how all of these terms fall together here. So really where we're headed with this is, how do we get the calculations, how do we get the math out of it? Okay, that's more what we're concerned with right now. Let's take a look at first, if we've got just a part of something here, okay, let's say that's 1/4 of an inch thick. So there's 1/4 of an inch, let's just call it aluminum. Aluminum's pretty common. That's a thick piece of aluminum, especially if you're going to deal with aircraft. So, here, we take a gander at this, and inside of this thing there's current flowing. Okay, we know that because we've been through Ohm's law, and E equals I times R. Well, E is electromotive force, that's measured in volts. Okay, I is current flow, that's a measure of the amount of electrons that are moving, that's measured in amps. Resistance to current flow, okay, that's resistance, and we're going to measure that. I guess I should write that here. That's the slowing or stopping of those electrons from moving, resistance, and that is measured in ohms. Okay? So quite simply, E is electromotive force, that's going to push. Current is amps, that's the electrons that are actually going to move. And then resistance in ohms, that's what we're actually looking at here. So we've got current flow in here. We've got all of this occurring. We've got voltage pushing current. Because this thing's a piece of copper or wire or something like that, it's going to have resistance to the wire just because it's copper. And then from that, we want to make down in here eddy currents. Okay, we know they're going to be shaped like little tornadoes. They're going to get weaker and weaker as we travel down farther. But how do we get here where we've got some liftoff? Okay, this space in here is termed liftoff. How do we get currents from this edge right here down into this piece right here? Okay, we do that by the process of which you've already been reading about. Electromagnetic induction here. That's going to tell us this. If we're flowing current through here, by the overall makeup of this coil, we're going to have a fairly large magnetic field outside of that coil. Okay? Now it's going to expand and collapse with the alternating current. Okay, so if we've got alternating current here, we've got positive, we've got negative. If we start at 0, it's going to continue to travel like this forever. Okay? So we've got positive maximum, negative maximum, or opposite maximum, and we've got one wave to one wave. Okay? That's now where we get into frequency, and frequency is measured in hertz. So, anyway, we back up here, and we say, alright, we've got AC current, so this magnetic field is going to expand and collapse all the time. So as it expands and collapses, that's just this AC current going back and forth, positive to negative. So for a minute it's going to spin like this, then it's going to spin back like this, it's going to go back and forth like that. So that same thing is happening here. Current's going to go this way for a little bit, then it's going to turn around and come back this way for a little bit. So back and forth, back and forth, back and forth. Same thing's happening there. Same thing's happening there, so that same thing has to happen here. So we get magnetic fields and they dip down into this material. And in that material we have electromagnetic induction, meaning we flowed current here, magnetic field developed, now we're flowing current down here. These guys, whoops, are the eddy currents. So those are the eddies. So we've got our primary current, our primary magnetic field. This would be our secondary current, all the little eddies. And then each one of these little eddies makes their own magnetic fields. Okay, so it has an overall magnetic field, which is relatively weaker than the primary magnetic field, and also opposes. So if this guy here is spinning this way, when this guy's spinning this way, this guy's spinning this way. Okay, that's from Lenz's law. Lenz's law says, hey, if you got one thing spinning one way, you got to have something else spinning the opposite to counteract it. Okay? So, not really too concerned with all the terms right now. We're just more concerned with getting everything kind of around the basic theory of eddy current, how we've got some liftoff, and if we got this thing closer, these would get stronger. We pull it away, they get weaker. Kind of makes the world go round, or at least makes eddy currents happen for us. Okay? So, take a look at those terms, kind of take a gander at what we've actually got here for terminology, meaning we take electricity from one place and we're going to induce electricity in another place. Okay? And because of a material, you have these terms, okay? Mainly these two, but once you start talking about AC current, you get inductive reactance. There's no inductive reactance due to DC current, there's only inductive reactance due to AC current. Okay? So think about that for a second, and then we'll come back and talk more about calculations.